Welcome to our session on distributed stateful data loader for large-scale pre-training. My name is Linsong, and I will be co-presenting this session with my colleague Davis. So with the time, let's get started. So the first question I would like to share or discuss is, when we talk about data loader for large-scale LLM training, what do we really talking about, or what do we really expect from the data loader? So I think first and foremost, we want the data loader to be stateful and checkpointable. So just like your model state needs to be checkpointable, the data loader state needs to be checkpointable as well. So whenever you save a model, your data loader state is also saved. And whenever you recover from a checkpoint, both the model state and data loader states need to be recovered at the same time. We also want the data loader to be auto-rescalable. Training could easily take weeks or months, and there are tons of reasons that you might have to rescale your workload in the middle. So being able to rescale is also important. And of course, we want data streaming. We want little to zero overhead for shuffling. I will talk a little bit on this in just a minute. And of course, we want the data loader to be fast, and we want the data loader to be non-blocking. And how to do non-blocking, which is, for example, while saving the data loader state, we want the saving to be distributed and in an async form. So zero communication is involved. And we want to support some, training features like dynamic data mixing. Dynamic data mixing is training, and sometimes during different stage of training, we might need different data mix ratio. Especially in the annealing stage, we might need a very different mixing ratio or even completely new data set. So we want to support all these training features. And of course, we want it to be PyTorch native, so we can just take the data loader around and plug into different code base or repository. But there's one more bullet point I want to add here, which is we think the data loader should be able to survive with this fast-changing world. I want to elaborate a little bit on this part. We just mentioned shuffling on the third point. So I think all of us here are very familiar with shuffling. We either use some built-in shuffling or we write our own shuffling for the data. However, all of these more or less rely on some in-memory data buffer in order to do proper shuffling. And that in-memory buffer tends to grow linearly with the amount of data you have in order to do true global shuffling. So this wasn't an issue in the past, but now this might become a problem because this year many of us has been following, let's say, Llama 3 family. We realize the importance of data, so we move from 2 trillion tokens to, let's say, 15 trillion tokens. So as I mentioned earlier, it grew linearly with the data. So your data loader might start slowing down or stop working. So how can you resolve this? You can, of course, design something that works with 15 trillion, but what if next year we have to deal with 30 trillion, 50 trillion, or 100 trillion? So we need some forward thinking, and that forces us to start thinking if we can build something that is zero overhead for the shuffling that can deal with arbitrary amount of data. So that's just one example of, the world is changing fast, so we need some forward thinking to build the data loader so it can not only survive today, but also survive for tomorrow. So with all of this in mind, we build our data loader that we have been prone to run for a few months on hundreds of small and large jobs. And we've been observed very stable throughput numbers, and the whole data loader is being async and non-blocking. So the training is not blocked by the data loader at all, as everything is async. So for the rest of the session, we will talk about our journey on how we build this data loader, We will do this in a timeline-based fashion because, well, hopefully this kind of timeline-based storytelling can make this a little bit more interesting, and also hopefully some of you could relate some of our experience or our pinpoint and find this useful. So with that being said, I will have Davis talk about our journey. Yeah.
Thanks, Linsong. So yeah, here's our data loader journey over the last year and a half with the timeline and all of our major milestones. I'll be taking us on a whirlwind tour, again, not just to describe what the process was like for us, but more to illustrate the kinds of decisions and issues that you need to handle when it comes to distributed data loading more generally. And we'll start at the very beginning with the ability to save and load from checkpoint mid-epoch. Now, when you're training an LLM on terabytes of data, odds are you may not even finish a single epoch by the time your training concludes. And so that means that if we want to resume from checkpoint, we have to maintain our data ordering and make sure that when we resume streaming data, we are not revisiting any of the data that we've already seen. Now, at the time, there weren't any data loaders out in the open that could do this for us. There were checkpointable, non-distributed data sets and distributed non-checkpointable data sets, but nothing that could do both. So we took the simplest possible approach to start with and added an argument to PyTorch's existing distributed data sampler that describes how many samples have already been generated. And I've included the code for this here, not to make you read any of it, but just to illustrate that this really was the simplest possible starting solution. We only really added 4 lines of code. And these 4 lines of code actually did do the trick and got us what we needed for at least a few months. But eventually, we realized we had a flexibility problem. The distributed data sampler approach only works when the data is indexable because it samples over indices, and text data is not cleanly indexable. Now, multiple stages of processing are required to massage a text document into a training sequence, and many of those stages require splitting or combining items, destroying any sampling scheme that you may be working with. So what we really need are composable, iterable data sets. And so here's a basic example on the kind of structure that we're working with. We can think of our data loader as a multi-stage pipeline, or equivalently as a series of wrappers. Each stage or wrapper is an iterator containing at least one sub-iterator. When called upon to yield a value, each layer calls its sub-iterator some number of times. It could be once, it could be multiple times, or even none at all if there's an internal cache that needs clearing, for example. But regardless, it gets input data from its sub-iterator or internally, applies a transformation, and then yields the transformed data to the next layer, which repeats the process. So to illustrate, on the right is a classic text data pipeline. Let's say you start off with a base reader that simply reads documents from disk. This is our base iterable, which we can then wrap in further layers to add processing steps in sequence. So for example, after you read a document, you may want to mix it with documents from other sub-datasets according to some predefined mixing ratio. So that means sampling over, say, multiple base readers according to a given ratio inside the data mixing layer, which will then yield a collection of documents. Once you have your collection of documents, we need to pack and slice them together to create training sequences of constant length. So that means fusing short documents together into a single sequence, taking long documents and slicing them apart into multiple sequences, and handling fractional documents at the boundaries. So obviously you can see how the document indexing scheme completely falls apart here. And then once we have that, we can add further processing operations such as shuffling or splitting the training sequences into an input sequence and a target sequence, as in masked language modeling or causal language modeling, for example, MLM or CLM. And if you need more processing, you're free to wrap this object in further wrappers as desired. So to actually build this, we extended PyTorch's existing iterable dataset with the ability to wrap other iterable datasets, as I described before. We then leveraged the recursive iteration scheme to similarly handle saving and loading state. We're just passing state information up or down through the different layers and consuming or accumulating information as we go. And this reconceptualization allows us to support more flexible data pipelines, but now we come to a more concrete and practical issue. As Linsong said before, on a cloud computing cluster, resource availability may fluctuate. And obviously, we should try to make maximum use of available resources at all times. So this might require scaling your job up or down to a different number of GPUs when we resume from checkpoint. But it's not clear how we're supposed to do this when every worker maintains its own individual monolithic state. How can we load the same state to a different number of workers while ensuring that we don't revisit any scene data? So there are two insights that allow us to pull this off. First, not all state actually needs to be preserved when you rescale to a different number of GPUs. Things like RNG state, for example, can be dropped entirely, because what does it even mean to preserve your RNG state if you now have a different number of RNGs? It's just a nonsensical question. And in practice, we actually found that just about all scalars fall under this umbrella, and this allows us to very easily implement automatic handling of checkpoint rescaling. For each stage of the pipeline, your state is a collection of specially flagged class variables that you want to hold on to. So we ask the user to specify which are state flags that are scalar valued and that can be dropped when we rescale, versus reshard flags, which are lists or buffers that can be pooled and repartitioned as needed. In this way, the user specifies lists versus scalars, and the code handles everything else. So for a more concrete and intuitive example, on the right, we start off with 4 workers, and let's say that each worker has a state that is a list with 3 items in it. If we want to rescale to 3 workers, we can take the state across all 4 of our original workers and pool it together into a list of length 12, and then we can just redistribute those items to our new 3 workers so they each end up with a state that is a list that's now 4 items. Pretty straightforward. However, keeping track of what data is owned by which worker and what data we've already visited is more complicated. And that's where the second insight comes in. All lists can be rescaled in this way, regardless of what's actually being stored in that list. So theoretically, we can populate one of these lists with more sub-dataloaders. And when we do the rescaling operation, the total number of subloaders won't need to change. So to return to our example on the right, let's pretend that the blue bar represents our entire data set. The user specifies that they want to split it into 12 logical shards, or 12 partitions. The dataset creates a base reader for each of those 12 sections, and then we assign those logical shards to the different workers, in this case 3 per worker. Each logical shard maintains and keeps track of its own state, and the worker just samples over the different logical shards at runtime. Now, if we want to rescale down to 3 workers, we again just take this list of 12 logical shards and redistribute them over the workers. All of the logical shards pick up exactly where they left off, and the only thing that changes is the sampling behavior of the workers. So between these two insights, we can implement rescalability as just another layer of the pipeline. We put in a rescalability layer. The user specifies how many logical shards they want to split the dataset into, and from then on, you can load your checkpoint to any number of GPUs that divides your logical shard count evenly. The number of actual logical shards stays the same, which means we still keep track of what data belongs where and what data we've already visited without having to do any repartitioning. And of course, if you don't need rescalability, that's fine. Simply skip this layer. Now, around this point in the timeline, we started working with datasets that were larger than 8 terabytes, which was actually something of a magic number for us. Most of our training was being done on A100 clusters, which have 8 GPUs and 1 terabyte of RAM per node. That means that if you're training on 64 GPUs, you have 8 terabytes of RAM, and if your data set is less than 8 terabytes, you can cache the whole thing, and life is easy. Unfortunately, now that we're working with data sets larger than 8 terabytes, we need to switch over from a caching paradigm to a data streaming paradigm, where each worker pulls one file at a time, exhausts the file, and then moves to the next. The problem with this approach is that it implicitly imposes an ordering onto the data. Finishing each file before starting the next limits the amount of stochasticity and randomness that we can inject. So we can save substantial memory by streaming data, but we need a dedicated shuffling layer to make up for it. And the way that you implement that shuffling does matter. So ideally, we'd like a uniform distribution over all possible data permutations, but it's not really possible if we're skipping from one file to the next. Instead, a common approach is local window shuffling. Populate a large but finite-sized buffer, uniformly shuffle the contents, and then form a new window and repeat. So on the right is a graphical illustration. In each of these scatter plots, the y-axis represents the original data ordering, and the x-axis is the order after shuffling. Excuse me. So the top plot is an example ideal case, uniform scatter of 1,500 data points. I'll note that any 2 consecutive data points will be separated after shuffling by, on average, 500 time steps. The middle plot is local window shuffling. Here we have uniform shuffling within each of our, in this case, 5 windows because we're using a window size of 300. but nothing between the windows. And the mean distance between originally consecutive data points in this example falls to just over 100. Not great. We implemented a better scheme based on a shuffle buffer. You have a buffer of values, and at each time step, you simply swap out one randomly selected value with the new input data, and then you yield the value that you overwrote as the output. And when we do this, the scatter plot on the bottom shows what happens. You can see that visually it's more diffuse, and we confirm this mathematically with the fact that any 2 points that start off next to each other are now separated by just under 300 time steps. So our buffer shuffle can maintain the same level of stochasticity as local window at 1/3 the memory cost, at least as measured by this consecutive point distance metric. So we removed the CPU memory bottleneck by switching over to data streaming with local shuffling, which is also nice because the setup time improves a lot now that we don't have to cache the entire data set before every run. The last thing we needed in terms of functionality was dynamic data mixing. LLMs are frequently trained on finely tuned mixes of different data sets, with the mixes varying depending on the different levels of subdataset size and quality. In research context, we may want to try tuning these mixtures, ideally without having to reprocess the entire data set every time. Thankfully, our existing framework makes it easy to add this functionality. Again, it's just another stage in the pipeline. The user provides a list of subdatasets and the desired mixing ratios, and our data mix layer wraps that in one iterator and follows the desired sampling ratios. I'll note that we're not just randomly sampling at that ratio in expectation. We actually track the token counts and make sure that we're following the desired ratio as closely as possible at all times. That way, the user can halt training whenever they want and know that the data mixture is still correct. And most importantly, we can try out different data mixes without having to reprocess multiple terabytes of data in advance. Now, so far, all the stuff I've discussed has covered practical issues, how to implement basic functionality and make sure it runs correctly at the desired scale. What I haven't discussed is speed. So at this point, we'd crafted a data loader which was practical and algorithmically correct, which is what we needed, so we turned our attention to our training code and squeezing out as much performance from our GPUs as we could, particularly through FSDP. But as Linsong mentioned before, after several months of improvement, we began to notice odd slowdowns, asymptotic decays in our training speed. Here's one example. Note that after reloading from checkpoint, we reattain our original high throughput, but then it immediately starts to slowly decay again. And it turns out this was because of CPU contention. Recall that each worker is streaming data from file to file. We're relying on our buffer shuffle to mix data between files, but in the base reader, we're also scrambling the order of the files and the order of all the documents within each file. And the easiest way to do this kind of random walk over files and documents is by stepping through a pre-shuffled list of pointers. That's how we were doing it. I'm pretty sure how PyTorch still does it today in their data loader. You assemble a list of indices or pointers, shuffle it, and then hold on to that list so you can step through it. But again, once you hit multiple terabyte data sets, these lists can become millions of entries long, and maintaining these lists is what's causing this slowdown. So how do we do a random walk that is n samples from n items without replacement, without materializing this list of pointers? And this ended up being a kind of fascinating minor foray into cryptography for us, and we ended up adapting material from the classic Art of Computer Programming by Donald Knuth. We implement an LCG, or linear congruential generator, which is one of those add, multiply, remainder, discrete logarithm class of operations. So using our custom LCG, we can implement a random walk over any number of items while tracking only 3 scalars: the random seed, the number of items we're stepping through, and the last item that we visited. And I'll note that all 3 of those values are values that we were already keeping track of in our data loader to begin with. So using LCG, we can drop our overhead from shuffling documents and files from hundreds of gigabytes over all our workers and nodes to literally 0. And here we have a visual comparison. On the top is the same ideal random permutation of 1,500 data points, and on the bottom is the same shuffle implemented with LCG. Now, if you look closely, there are some diagonal striations indicating some very loose pseudo-periodic behavior, but on the whole, I mean, it looks pretty good, and more importantly, we can implement it without massive memory overhead or CPU contention, so that FSDP isn't bottlenecked anymore. And this fixed the problem. Our throughput stayed high until we managed to get Torch compile working with FSDP, and again, this same asymptotic slowdown came right back. And again, the problem was CPU contention, but this time it had to do with how we were doing checkpointing. So most training pipelines do their checkpointing through a checkpointing utility. You grab the model state, the optimizer state, and now the data loader state, and you pass them all to the checkpointer, which writes it all to disk. But this means that in a naive implementation, you're putting the model and the optimizer and the data loader all on the same process, that you can fetch all those states on demand. But this means that they can block each other. Essentially, they're running in serial rather than in parallel, as in the top row here. So it almost doesn't matter how fast the data loader is, because there's always going to be some blocking and some slowdown. Now, the PyTorch data loader does have built-in multi-process support, so because we built everything in PyTorch, it was easy to move the data loader onto a separate parallel process. The wrinkle is that once we do this, it runs asynchronously, so we can no longer grab the state on demand for the checkpointer. Our solution was to make checkpoint handling, you guessed it, just another stage of the pipeline. The checkpoint layer is a pass-through layer that does not transform any data, but instead handles checkpoint saving and loading at startup and every end steps. And this allows us to move everything off the master process so that we can get the full speed of FSDP and compile at the same time. Now, more recently, we focused on improving flexibility and quality of life. The original data loader only supported PyArrow file formats because this file format supports efficient fractional loading of individual documents and document slices in the case of large files or very long documents, but definitely a non-standard format. So we now provide arbitrary support for any file type via a file handler class stub. The user implements just 4 basic operations: open, length, get, and slice, and now the data loader can handle it. And you can also bundle a tokenizer into your file handler for processing raw text. And we did this. We can now consume many Hugging Face datasets with no slowdown observed. And finally, to be proactive in handling future developments, we want to support multiple data loaders per GPU. And this actually requires a fairly intensive change, because the way that PyTorch handles this currently is to instantiate the whole data set, pickle it, and then send that to all of the workers. Now, if we're doing our data partitioning during initialization, then all of the workers associated to the same GPU will get clones of the same partition, which is not what we want. We want to partition our data over all the available workers, with every worker getting a unique partition. So now we actually defer all of our setup until after initialization and pickling. And when the data loader lands on the worker, it uses the worker ID to perform adjusted partitioning and setup. And this enables massively parallel asynchronous operation, which could be critical for future developments such as multimodality, for example. And that's the last year and a half in data loader development. The latest milestone, in fact, just landed last month. So what's next for this month and beyond? Well, at this point, we consider a world-class data loader for LLM pretraining, and we're currently working on contributing it back to PyTorch. We have an open PR plugging this virtually as is into Torch Titan, which is a surprisingly easy process that Linsong will be discussing some during the Torch Titan talk tomorrow. We're also working with PyTorch on how to land pieces of this more generally. The data loader itself is clearly built for strictly LLM pre-training on raw text data only. But pieces of it are much more broadly applicable. In particular, I think the stateless shuffle and the auto rescaling logic. And of course, internally, we'll continue to rely on and improve upon our data loader as we upgrade our training pipeline to things like FSDP2, FP8 training, new hardware support, and so on. So in conclusion, the better and better we get at utilizing our GPUs, the more the other bottlenecks begin to matter, not least of which is data loading. Hopefully, we demonstrated that handling the data loader side of the equation takes substantial and thoughtful design and effort. But what really helps and makes it a lot easier is having an open and extensible framework to build off of. So a big thank you to PyTorch for providing us with exactly that, and to you all for sticking with us through a long day of talks and presentations. Thank you. Unfortunately, I think with time, we don't have time for questions, but we'd be happy to chat offline.